Hello, in this video I'm going to talk about an important theorem in Euclidean geometry called Ceva's theorem. First, let us have a look at the content of today's video. Okay, first I will define the notion of a Cevian. Using this definition, I will be able to state Ceva's theorem for you. And of course, naturally, after the theorem, I will present a proof for Ceva's theorem. And then I will present an example that you can use Ceva's theorem to solve it and prove it. Usually, it's called trigonometric form of Ceva's theorem. Sometimes people also consider this as an important theorem. But of course, I bring it here as an example. And then, as you will see, Ceva's theorem is related to a theorem about some concurrency point. This concurrency point lies interior to the triangle. I want to discuss about what will happen if this concurrency point lies exterior to the triangle. So I want to view this problem from different perspectives. And after that, eventually, I will just show you one or two slides about actually who discovered this theorem, about the history of this theorem. Okay, let us first define a Cevian. What is a Cevian? A Cevian is actually a line segment that joins a vertex of a triangle to an interior point on the opposite side. That is called a Cevian. For example, consider this triangle ABC and just pick a point on BC and join A to X. Then AX is called a Cevian corresponding to A. Here in this picture, you see that BY is a Cevian line corresponding to vertex B, and CZ is a Cevian corresponding to vertex C. Yes? So here, this picture shows you three Cevian lines corresponding to different vertices of your triangle. Okay, now using this notion, I will be able to state Ceva's theorem. Ceva's theorem actually is this. If in triangle ABC, AX, BY, and CZ are concurrent Cevians, corresponding to vertices A, B, and C respectively, then this very nice relation holds. The ratio of BX over XC multiplied by CY over BYA multiplied by AZ over ZB is exactly equal to 1. Okay? So let us now go to the board and try to discuss about a proof for this theorem. Okay, so as you see, I have actually drawn a picture here for you. So somehow it captures the essence of the Ceva's theorem. So let us see what is the content of Ceva's theorem. So here I have a triangle ABC, and I have three Cevian lines, Cevians actually, AX, BY, and CZ. But they are concurrent at some point M. If this happens, I want to prove that BX from here to here divided by XC multiplied by CY over YA multiplied by AZ over ZB is exactly equal to 1. So this is the claim, this is the assertion actually in Ceva's theorem. To be able to prove this, let me just remind you about some properties that we had before. So one of them is about the ratios. So if I have a fraction alpha over beta equals to another fraction A over B equals to another fraction C over D, okay, then I can conclude, if I want to, that the first fraction, for example, is equal to if I add the numerators and do the same thing for the corresponding denominators. So that, what does it mean? It means that if you take these two fractions and set up a new fraction in this way, that you are adding the numerators and you are adding the denominators, yes? You will face a new fraction which I claim is equal to the values of these three fractions, because all of them are the same. And I want to show that this is also the case if you have a minus c over b minus d. Okay, it's very, very simple, but I will use this several times in the proof of this theorem, so I want you to understand it once for all here so that I can use it freely when it comes to the proof of the theorem. Okay, so why is that correct? Okay, I am telling you that these three fractions are the same, so I am allowed to give them a name, a common name. So let me call the value of these three fractions to be k. Okay, then what you say, a over b is equal to k. What can I conclude? I can conclude that, okay, a is equal to k times b. You are also telling me that c over d is equal to k. So what does it mean? It means that c is equal to k times d, yes? Now, let me start with this new fraction that I made. So I would say that a plus or minus c divided by b plus or minus d is equal to, instead of a, I put kb, instead of c, I put kd, and of course I have plus or minus here, and then in the denominator I'll have this. And then you can immediately see what happens, because now I can factor a k out, and this becomes b plus or minus d divided by b plus or minus d, but whatever this is gone, and what is left for me is just k. So if you let me to give the name of these fractions to be k, I just showed you that the value of this fraction that I set up using this method is also k. So this means that that is true. So this is a very important thing. So if you have the equality of three fractions, you can say that the first fraction is equal to a new fraction constructed in that way. Of course, you have to be careful that b minus d, for example, is not 0, b plus d is not 0, and of course, in those cases, we will have those cases here in this problem. Okay, so that is one thing I want to use. The next thing is actually something we had on the previous videos in this playlist, and that is this. So if I have a triangle, say ABC, and I just concentrate on one Japian. So let me put a random point here, x on BC, and then set up this Japian. Okay, this Japian will partition my triangle into two triangles, the left one, the right one. So let us assume that the surface area of the left one is S1, and the surface area of the second one is S2. What I am claiming is if you take BX, which can play the role of the base for this triangle on the left, and then divide it by XC, which can play the role of the base of the triangle on the right, this becomes exactly equal to S1 divided by S2. Yes? We already had this, but it doesn't hurt if I just fresh up your memory about that. So why is this true? Because, for example, if I want to calculate S1 and S2, I need the height. So let me just draw this height. For the triangle ABX, I draw this height. I drop a perpendicular line, AH, and let me call the length little h. Okay, so then what happens? S1 over S2, so I can write S1 over S2 is equal to, instead of S1, I can write 1 over 2 times the height times the base. So it becomes 1 over 2 h times bx, and I divide it 1 over 2 h times, because for this triangle, hopefully you agree, that this plays the role of the height as well. But of course, because this angle is an obtuse angle, you would expect that the height is actually lying exterior to my triangle. But anyway, this is exactly the height of this triangle, but the base is XC. So this becomes xc. And then you immediately see what happened. This 1 over 2h and 1 over 2h are cancelled. And I will get with bx, I'm left with bx over xc. So this means that I was able to show that bx over xc is equal to s1 over s2. Okay, similarly, what happens if I ask you what is s2 over... So let me write it like this. I will take s1, but instead of dividing it by s2, let me this time divide it by the total area. So total area in this case is s1 plus s2. So what do you think I will write? I will not prove it because the proof is exactly the same. So if you want, we can prove it. So what is s1? S1 is again 1 over 2 h times bx, but s1 plus s2 is the total area. Again, this is the height of the bigger triangle as well, but the base will be BC. So this becomes 1 over 2h times BC, and this time this is gone, and what is left for me is BX over BC. Yes? Okay, so this means that if the heights of two triangles are the same, so the ratio of the surface areas is exactly equal to the ratio of the corresponding bases of those triangles. So I will also use this extensively in the proof of this theorem. Okay, now let us go to see how we can use these two to prove this theorem. And the proof, by the way, is actually very simple but very nice. Okay, so how should I do that? The goal is to calculate these fractions in terms of some areas in this triangle, because you see that these Cevians have partitioned my triangle into 6 smaller triangles. So somehow I want to find the right combination. What do I mean by that? I mean, I would write bx over xc. Here, let us just try to focus on one Cevian ax and this left-hand side triangle and this right-hand side triangle. Okay? So let us just concentrate on that. Exactly because of what I described, you can immediately write this as the surface area of the triangle ABX. Yes, because BX is the base of that triangle, over the area of this triangle, ACX. This is on the one hand. But on the other hand, just please ignore in your mind the top view and just concentrate on this triangle here, MBC. Again, MX is a Cevian, and partitioning that triangle into 2 pieces here. I can use the same thing, and I would say bx over xc, ignore this momentarily, is equal to what? The area of this triangle, which is BMX, over the area of that triangle, CMX. Yes? This is exactly so. This one comes from the comparison between these 2 triangles, and then this one comes from the comparison of these 2 triangles. Okay, but now I have 3 fractions that are equal, so I can use the first rule, yes? So what was the first rule? The first rule tells me that if I have 3 fractions equal, write the fraction, put equality sign, and subtract these 2 numerators over subtraction of the denominators, corresponding denominators. So I will do the same thing. So I can conclude here that the first fraction, which is this one, is equal to the difference between these 2. So this becomes the surface area of ABX minus the surface area of BMX, yes, over the surface area of ACX minus the surface area of CMX. Okay, but now one step forward. Let us see. I can conclude that. I copy and paste this part, bx over xc, but now let us look, what can I write for the numerator? In the numerator, I have the triangle ABX, A, BX, this is my triangle, the surface area of this triangle, minus the surface area of triangle BMX. BMX. So hopefully you agree that if I take this away, what is left is ABM, the surface area of triangle ABM. Yes? Over, I will do the same thing, similar thing here. ACX, this triangle, surface area of this triangle, minus the surface area of CMX, which is this triangle. So if you subtract them, what is left is AMC, yes? Or ACM. Yes, this would be this triangle. Okay, as you can guess, probably I will do similar thing for the middle fraction, but then you have to look at the picture from the right-hand side and giving the role of bases here to these line segments CY and YA. So if I look at the problem from this side, and then I will consider BY as my Chevian, which is partitioning the original triangle into triangles ABY and BYC, yes? But more or less everything is the same. So if you don't mind, to learn this better, let me just do the middle one in full detail, and then I will ask you to guess what will happen for the third one. But of course, guessing is not good. If you don't understand, I will recommend you to sit down and do it explicitly yourself. But of course, you will understand what's going on. Okay, so what I want to do, as I told you, let me just a similar thing for it. By the way, if you don't mind, let me put this in a box and call it number 1 because I will use it. Okay, so here for CY over YA. So what can I do? Let me start writing from here. So CY over YA. CY over YA is equal to the surface area of this triangle, which is BCY, over surface area of this triangle, ABY. On the one hand. On the other hand, I concentrate on these two smaller triangles, MYC and MAY, because this also can play the role of the base of this smaller triangle. This can also play the role of the base of this smaller triangle. So on the one hand, CY over YA is equal to this. On the other hand, it is equal to the surface area of CMY, yes, over surface area of AMY. Yes, and then again, I want to use that trick once more. So what I can conclude, I copy and paste this part, and I want to do it in my head. I want to do the same thing. I want to do the subtraction in the numerators, do the subtraction in the denominators. But if I take this out from this, what will happen? BCY is this triangle that you see here. I am supposed to take CMY away from it. So CMY is this part. So what is left is BMC. The surface area of BMC divided. I will do the same thing for the denominators. So this is ABY minus AMY. So what is left for me is AMB, or ABM. Okay, so S of ABM. By the way, to keep consistency, if you don't mind, let me also write it BCM. Of course, it doesn't matter. These are the names for the triangles, but I think it would be better if I write it in this way, in a consistent way. So that's number 2. Okay? And now what happens? Hopefully you will see, without doing the details, what will happen if I write AZ over ZB. I really want you to be able to do it yourself, but here, if you do it correctly, if you follow these steps, what you will get will be the S So I will try to look at the problem from this side, and I will give the role of Japian to CZ this time. So if I do AZ and ZB, AZ is related to this triangle and that triangle. So if I subtract them, ACM is left. And if I do the same thing for here, what will be left for me? This triangle, I take this part out of it, so BCM is left. Yes, and then I will give this number 3, the name number 3. And now hopefully you understand what is supposed to be done. I want to multiply these. So I would say that the left-hand side of Ceva's theorem is equal to, instead of bx over xc, I plug this in. So it is s of ABM over s of ACM multiplied by, the middle one is s of BCM over s of ABM, and finally s of ACM over s of BCM. Yes? And now look, this first numerator is cancelled by the denominator in the second one. The denominator of the first one is cancelled by the numerator of the third one, and similarly these two are cancelled, and I get exactly 1, which is equal to the right-hand side of Ceva's theorem. So it's a very nice relation, and it's a very good theorem because you have infinitely many degrees of freedom, yes? Because these Cevians are completely arbitrary, except that they have to be concurrent. If they are concurrent, then it doesn't matter how you draw them. For every triple, you will have this rule. Okay, so that's a very nice and I think powerful theorem. But of course, the main strength of Ceva's theorem is not the Ceva's theorem itself, it is the converse of the Ceva's theorem that will be the content of the next video, okay? But for the time being, let us try to understand this by solving an example. Okay, so the example that I want to mention, usually it is called trigonometric form of Ceva's theorem, and let us see what is the content of this. So the setup is exactly the same setup as we had for the Ceva's theorem itself. AX, BY, and CZ be concurrent Cevians in triangle ABC corresponding to vertices A, B, and C, respectively. What we want to show is this. We want to show the sine of this angle over the sine of this angle multiplied similar expressions is equal to 1. So it is very similar to Ceva's theorem, but of course it includes sine of angles, so this name is a very natural name. It's like Ceva's theorem, it's the product of 3 fractions equal to 1. On the other hand, it is involved with trigonometric functions, so trigonometric form of Ceva's theorem is a good name, I think. Now we want to prove this, okay? Okay, so I have written it down here. What we want to prove is this relation, okay? So, if you don't mind, because writing so many letters is actually hard, let me give them names, yes? So here, BAX, which angle is BAX? This is angle BAX, so I will call it this angle alpha 1. And then CAX is this angle, so I will call it alpha 2. And then I go here, CBY, I will call it beta 1. And then ABY, I call it beta 2, for simplicity of writing only. And then ACZ, I call it gamma 1. And then this one will be gamma 2. So what I want to prove is to prove that sine of alpha 1 over sine of alpha 2 is equal to times sine of beta 1 over sine of beta 2 times sine of gamma 1 over sine of gamma 2 is equal to 1. So in other words, I want to show that the product of sine alpha 1, sine alpha 2, sine alpha 3, sine alpha 1, sine beta 1, sine gamma 1 is exactly equal to sine alpha 2 times sine beta 2 times sine gamma 2, which is not trivial at all, yes? So if I take sine of this angle multiplied by the sine of this angle multiplied by the sine of this angle, it becomes, according to this trigonometric form of Ceva's theorem, exactly equal to the product of the sine of this angle, the sine of this angle, and the sine of this angle. That is what we want to show. Okay, but to prove this, I need to remind you about another property. So if you want to find the area of a triangle, so let me just concentrate here. So if I want to find the area of this triangle, ABC, so let me just draw this as a height, okay? And then this angle is, let me call it theta. And then you immediately see that, for example, if I ask you what is the height, height is equal to the length of AB multiplied by the sine of theta, yes? Or in other words, sine of theta is equal to the opposite side in this right angle triangle divided by the hypotenuse, so it can be written in this form. But if I ask you what is the surface area of that triangle ABC, you will tell me that this will play the role of my base, so it becomes 1 over 2 times AC times the height h, which is equal to AB sine theta. Now, if you look at this way of reading this surface, how does it look like? So it is 1/2. Two sides multiplied, you see AB and AC are multiplied, and then I have sine of theta, which is the angle, theta is the angle which is contained between these two sides that I chose to write the product here, yes? So, in other words, if I want, this is called, by the way, the sine rule, yes? The area rule. So the area rule tells you another way to calculate the area of the triangle. You write 1/2, you take two sides, multiply the lengths together, and then you multiply it by the sine of the angle contained between those two sides that you have chosen for the multiplication. Okay? So I want to use this idea here. So how can we do that? So here, again, so let me just okay, so here again I write bx over xc, and we know that bx over xc is equal to this area abx over acx. But according to what I just told you, the area of abx can be written as AB times AX times sine of alpha 1, which is contained between these two lengths, and then multiplied by 1/2. So let me just write 1/2 side AB multiplied by side AX multiplied by the angle between side AB and side AX. So don't get confused. BX over XC, on the board you see that BX over XC is equal to this. So I copied and pasted BX over XC here. Instead of the area of ABX, I am writing this expression. Okay, and then divided by the area of ACX using the similar area rule. ACX, I will multiply 1/2 by AC, and then multiply it by AX, and then multiply it by the sine of the angle between AX and AC, which is alpha 2. Yes? And then what happens, this 1/2 and that 1/2 are gone, this AX and that AX are gone, so what is left for me is that BX over XC is equal to AB sine alpha 1 over AC sine alpha 2. Yes? So this is relation number 1. But I can take this one from the board, CY, this one, this middle one, CY from YA, copy and paste that part. But instead of this area of BCY, I can write BC multiplied by BY multiplied by the sine of the angle between them, which is beta 1, and of course multiplied by 1/2. So this becomes 1/2 BC BY sine of beta 1 divided by the area of ABY similarly will be 1/2 AB times BY, this time times sine of beta 2. And then again, what happens? This 1/2, and this BY and that YY are gone. So what I get is CY over YA equals to BC sine beta 1 over AB sine beta 2. So this is number 2. And if you don't mind, let us just guess what will happen for number 3, because that is completely similar. So if I use that relation up there, AZ over ZB, this becomes equal. Instead of this area, I can write 1/2 AC times CZ times sine gamma 1, and then I divide it by 1/2. So this will be BC CZ sine gamma 2, yes? Yeah, actually I calculated that for you. So, and then what happens? This 1/2, that 1/2 are gone, CZ and CZ are gone. So what is left is AZ over ZB is equal to AC sine gamma 1 divided by BC sine gamma 2. Yes? Okay, so this is number 3. Okay, and then hopefully you understand what we're supposed to do. I will take 1, 2, and 3 and multiply both these sides together. The left sides and the right sides. Yes, the right hand sides, the left hand sides. So if I do that, I will get BX over XC multiplied by CY over YA multiplied by AZ over ZB. And on the right hand side, if I multiply these fractions, you have to be a little bit patient. See sine alpha 1 divided by AC sine alpha 2 multiplied by the second fraction is BC sine beta 1 divided by AB sine beta 2, and then multiplied by the other one, AC sine gamma 1 over BC sine gamma 2, yes? Okay, so I realized that the product of these 3 fractions should be equal to the product of these 3 fractions. But according to Ceva's theorem, this product is exactly equal to 1. And on the right-hand side, the expressions that I don't need are cancelled out. So you see AB here and AB here are cancelled, BC here and BC here are cancelled, AC here and AC are cancelled. So what is left for me is sine alpha 1 over sine alpha 2 is equal to sine beta, multiplied by sine beta 1 over sine beta 2 multiplied by sine gamma 1 over sine gamma 2. And that is what you wanted to show. That's the trigonometric form of Ceva's theorem. Now the point is that all these Cevian lines are lying inside the triangle. And by the way, that's the definition of a Cevian. But you might assume that, is it possible to say something concrete if one of the Cevians or 2 of them lie outside at the triangle, even though they are not Chavians. If you don't mind, let me just invent a word. Let me call them Pseudo-Japian lines. Okay, so because by definition, Chavian should connect a vertex to a point on the opposite side. But now my point is that if instead of connecting a vertex to the point on the side, I extend the side from one direction and then pick a point on the extension and connect it to the opposite vertex. So let me call that a pseudo-Japian line or a pseudo-Japian. Okay, we want to discuss about this scenario, if there is something we can say about it. So, what happens if the concurrency point lies outside? Okay, this is one scenario. So you see I have A, B, C here. This is my triangle. This is my Japian line, but you see I am considering this to be a pseudo-Japian line. So you see AC is my line. I extend it from this side and pick a point B, Y there. And then this is my side. I extend it from this direction and I put a C here, so I put a Z here. And then this is a pseudo-Japian line. And this is also a pseudo-Japian line. And that is a Japian line. But I have drawn them in a way that is still, if I continue this one, they will actually intersect at one point, so they are still concurrent. So the continuation of AX and BY and CZ are still concurrent at the same point M. Okay? Okay, you see that this picture is different from the original one, but the question is that, do you think still that that relation holds? Interestingly, the answer is yes. So even if in this setup, which is different from the original Ceva's theorem, still this will work. I can consider other scenario. For example, here, this is my ABC again, but what I have done, I have extended AC and AB from A side, not from B and C sides. Yes? So again, I have this Japian BY, but this is a pseudo-Japian. And this is also a pseudo-Japian. If I continue these pseudo-Japians and this Japian line, I have drawn them in a way that still they intersect at a single point. I am not saying that this is always happening, but I'm saying if this happens, you see this setup is different from the setup that we had, yes? But still, interestingly, the rule is the same. Okay, so you see that this is different. For example, bx over xc is the same thing we had in the original version, but cy over ye, these are different because cy is this length over ya, which is this length. And az, which is this length, divided by zb, which is this length. So I want to, so here I want to show that still this is the same. The last situation that might happen is this scenario. Yes, so I have actually extended AB from B side, and I have extended AC from A side. Yes, and then again, I have this Japian and this pseudo-Japian and this pseudo-Japian. I have drawn them in a way that still they intersect, but still the result holds, even in this setup. So in principle, you see here, these are three scenarios that I can imagine, not more than that. So I extended AB from B side, I extended AC from C side. I extended both AB and AC from A side. Here, I extended AC from the A side and AB from the B side. Yes? Interestingly, in all of them, still the same relation holds. There is some minor changes to the proof. So if you don't mind, let me just do this middle one in detail so that you can see the differences between the proofs. But the good point is that this same relation, okay, holds. But of course, these might refer to different lengths, yes? But anyway, the way that you write the relation is left intact. Okay, let us go back to the board so that we can discuss about only the middle one. You can work out the first and the third one yourself. Okay, so I have drawn the middle picture here on the board for you to see what can we do. What can we do here? So here I want to prove the same thing holds for this new setup. Okay, so I will do the same thing. So you see, I will start from bx over xc. So here bx is the base of this triangle on the one hand, and the base of this triangle on the other hand. xc is also the same. It is the base of this triangle on the one hand, and it is the base of this bigger triangle on the other hand. So bx over xc can be written as the ratios of these two and those two. Okay, so what can I do? I would say that the surface area of abx over the surface area of acx, let me write it in order. And on the other hand, I can concentrate on the bigger ones. I can write bmx and then for this one I can write cmx. Yes? And if you see, by the way, compare this one with the one that you see on the board. They're identical actually, even though the setup is different, but what you write is identical. Okay, but then you can conclude that, okay, bx over xc is the difference between these two. This time, this one is the bigger one. So bmx minus abx, so this is bmx minus abx, taking this out. So what is left is just this narrow triangle that you see here is left, yes? So that is ABM. AMB, let me write as before, okay? And then if I do the subtraction here, so what is left for me here is that S of ACM. So nothing changes at all. Of course, the setup is different, but the writings are the same. That's number one. Okay, now let us go to number two. I want to write CY over YA in this setup. CY is from here to here. YA is from here to here. Okay, now look below. What happens? CY can be viewed as the base of this bigger triangle. So I would write CY over, and then YA can be viewed as the base of this narrow triangle here. So CY over YA can be written as S, the ratio of two S's. So the S of triangle A, triangle BCY over the ratio, over the surface area of ABY. Yes, and this can also be written as, this is on the one hand, okay? So let us check here. So is there something different? No, you see the middle one BCY, BCY, and ABY, ABY. So it is also surprisingly the same. Okay, and then I go to the next one. On the one hand, look above this line. CY can also play the role of the base of this top triangle. Okay, and YA can also play the role of this top triangle again, the narrow one. So what can I do? I can write the surface area of CMY over the surface area of AMY. Yes? CMY, AMY. Again, surprisingly, this is exactly the same thing. Yes? Okay, so what you do? But this time, if you subtract, you will be in trouble. Yes, because if I take this one and subtract it from this one, I don't know what to write for. for the difference, yes, because one triangle is in this direction, the other triangle is in that direction. I don't know what happens if I subtract them. But the interesting thing is that you remember the first lemma that we talked about is also working if I add them. This time we add them actually. But that was the only point that I want to mention. So cy over ya becomes equal to the sum of these two this time. Divided by the sum of these two. So this step is different from the previous one, but the result will be the same. So why is that? Because BCY, if I take this triangle and I add it to the surface area of CMY, what do I get? I get the area of the bigger triangle, which is BMC. Divided by ABY is this triangle, added to AMY, I will get AMB, the surface area of AMB. Yes? Now let us see what was the result before. The result is also the same. You see, BCM and BMC, they are the same. ABM and BMB are the same. But the way that I derived it is a little bit different. Instead of subtracting numerators and denominators, here, if I subtract, I will not get something tangible in my picture. But I realized that because one of the triangles, one pair of triangles is one side, the other pair is on the other side, it would be better if I add them. But when I add them, everything goes very smoothly and I get the same result back. Okay? And then here, if you want, you can continue to AZ over ZB. So again, AZ is from here to here, and ZB is from here to here. ZB from here to here. I will follow the same idea, but instead of doing from the left-hand side, I do it from the right-hand side. Again, I do the addition, but I will get the same result back. So this becomes S of ACM, S of BCM. And of course, if I am getting the same results back, when I multiply them, they will be cancelled pairwise, and I will get the same number 1 at the end. So that was crucial. I want you to understand, not the Ceva's theorem is related to Japian lines. By definition, Japian lines are lying interior to the triangle, so the point of concurrency naturally lies inside. But we can imagine pseudo-Japian lines, I don't know if it's a proper name for that, but then you can also imagine that this concurrency point M is no longer, for example, interior point. There is no guarantee that the theorem still holds, but miraculously we can see that this is holding in all possible scenarios that is conceivable. Yes? Okay. Now let us talk a little bit about the history of this, and then we end this video. Okay, this is interesting. This theorem is actually discovered first by an Arab mathematician, Al-Mu'tamin ibn Hud. And interestingly, he was a king actually of Saragossa, Spain, from 1081 to 1085. So this is a little bit less than 1,000 years old, yes? Okay, but this theorem in the West is famous by Ceva's theorem, named after Italian mathematician Giovanni Ceva, living from 1647 to 1734, and he discovered or rediscovered actually this theorem in 1678. Okay, so I hope that this video is useful for you and you have enjoyed seeing the proof. Until the next video, be safe and goodbye. Thank you.